All right, day 8. Let's talk about something that trips up so many people: normalization versus standardization. You hear these terms thrown around a lot and they sound kind of the same, right? But here's the thing. Picking the wrong one can seriously mess with your model's results.
So let's frame the problem with a super simple example. Say you've got two features for a person: their age, maybe 25, and their salary, say 70,000. Now, you and I can look at that and weigh them, but what does a machine learning model see? It just sees the numbers, and 70,000 is a way bigger number than 25. So which one do you think the model is going to pay more attention to, even if it's not actually more important?
And that's really the heart of the problem. A lot of algorithms, especially those that work with distances or gradients, are really sensitive to the scale of your features. The salary feature, with its huge numbers, can just completely overpower the age feature. It's not because salary is more important, it's just, well, it's louder. The model ends up listening to the scale, not the actual information, the signal.
Think about it this way. A change of 10 means something totally different for each feature, right? A 10-year age gap? That's huge. A $10 salary difference? That's nothing. It's just noise. But without some kind of scaling, the model has no concept of this context. It just sees the numbers, and the salary figures will just pull all the attention, creating a really skewed perspective.
So, what's our goal here? It's pretty straightforward, actually. We just need to get all of our features onto a common playground, a common scale. That way, age and salary can both contribute fairly to the model's decisions, based on how useful they actually are, not just how big their numbers happen to be.
Okay, so how do we do that? Well, there are two main ways to get this done. Two main paths to the same goal. To make this easy to remember, let's give them nicknames. First, we have normalization, which I like to call the squeezer. And then we have standardization, which we'll call the recenterer. One squishes, one recenters. Let's break down what that actually means.
So, first up, normalization, the squeezer. The whole idea here is to just, well, squeeze the data into a really small, predictable box.
The technical name for this is min-max scaling, and it works exactly how it sounds. You look at a feature, find the absolute smallest value. That's your new 0. Then you find the absolute largest value. That's your new 1. Everything else, it just gets proportionally squeezed to fit somewhere in between 0 and 1.
The result is nice and tidy. Every feature now lives in that same 0 to 1 range. But there's a pretty big gotcha. Because this whole process depends on the absolute min and max, it's super sensitive to outliers. Imagine you have one CEO in your dataset with a crazy high salary. That one person's salary becomes the 1, and suddenly everyone else's salary gets squashed into a tiny little corner, like between 0 and 0.05. You basically lose all the detail for the majority of your data.
Okay, so what's the alternative? That brings us to our second method, standardization, or the recenterer. Instead of just squishing things into a box, this approach is a bit more statistical. It looks to distribution of the data itself.
This one's also called z-score scaling. And instead of min and max, it uses two different numbers: the mean, the average value, and the standard deviation, which is a measure of how spread out the data is. For every single data point, it calculates a new value based on a simple question: how far is this point from the average in terms of standard deviations? The effect of this is that it recenters the whole feature so that its new average is exactly 0.
So what you end up with is a feature where the mean is 0 and the standard deviation is 1. And the huge win here? It's much better at handling outliers. That one CEO with the crazy salary, it'll just be a point that's maybe, 3 or 4 standard deviations away from the mean. It won't completely warp the scale for everybody else. It handles those extreme values way more gracefully.
Okay, so we have the squeezer and the recenterer. Two solid options. So the big question is, which one should you actually use and when? Well, the answer, as it so often is it depends. It depends on your model and on your data.
Let's break down the main differences. Normalization, our squeezer, forces everything into a hard range, usually 0 to 1, but it's super sensitive to outliers. Standardization, our recenterer, isn't so strict about the range, but it's way less sensitive to outliers and gives you that nice mean of 0. So it really boils down to, do you need a strict boundary or do you need to handle potential outliers?
So when is normalization a good idea? You'll often see it used with algorithms that don't really care about the shape of the data's distribution, but do care about the scale. A classic example is k-nearest neighbors, or KNN. It's all about distances, so having everything on that same 0 to 1 scale is really helpful. You'll also see it a lot in image processing or with some neural networks, where having inputs in a tight, bounded range can just make the whole training process smoother.
And what about standardization?
Honestly, this is often the safer default choice, especially for models that do have assumptions about your data. Things like linear regression, logistic regression, and support vector machines. They often perform better when the features are centered at 0. And for something like principal component analysis, or PCA, well, it's absolutely essential. The whole method is based on variance, so you have to standardize first.
But here's an important exception, a little pro tip for you. If you're working with tree-based models, so think decision trees, random forests, gradient boosting, you often don't need to do any of this. Because of the way they work, by making splits on one feature at a time, they just aren't sensitive to the scale of the features. So you can save yourself a step.
So if you need a simple rule of thumb, here it is. Normalize when you know your data has a fixed range and won't have crazy outliers. Standardize when you suspect you might have outliers or when your model benefits from data centered around 0.
The main takeaway is this: there's no single best method for every situation. Your choice really depends on your specific data and the assumptions of the model you're using. When in doubt, it never hurts to try both and see which one gives you better results.